So we're going to use what we know about acceleration directions. For a basketball that's just thrown straight up into the air, right? Just goes straight up and comes straight back down. And we want to know what the motion diagram looks like as the ball goes up, and then as it comes back down again, how it moves, showing the acceleration as it goes up, the acceleration as the ball comes back down, and then also at the top. Now we've done part of this before, but the first thing, of course, is to draw our sketch. So the ball coming upwards, and you have to think about, is it going to slow down, speed up, what do I know? Well, as you throw anything up in the air, it's going to slow down. So if it went this far to begin with, in the first second, the next second it's going to go a little bit less distance. Right, so it's going to slow down as it goes upwards, and then it's going to come back down again. Now, of course, if I threw it exactly straight up, it would come back down over the same spots. And so I'm not going to draw it again. Now, we're not sure exactly. We haven't talked about forces yet. So we're not sure exactly if on the way back down it's going to cover exactly the same distance every second, let's say. But certainly we know that as it comes down, it is definitely going to go faster and faster and faster. So these balls, actually, if I just drew it off to the side again, on the way down, it's not unreasonable to think about the ball coming back down, really following exactly the same path, and it could cover the same distance, but the same overall motion is definitely going to happen where it slowed as it went up and it increased speed as it went down. All right, so on the way up, we've done this before. I can just quickly draw the dots on the way up. I can draw the dots on the way down. Now, ideally, right, they'd be right on top of each other. The dots coming up and the dots coming back down, but I've just pushed them off to the side so I can see what's happening. And so really this spot and this spot, these are the same. All right, because they're at the highest point. All right, so given that I have the dots showing where the location is, I can draw in the velocity vectors pretty easily. Now I'm not drawing one across like this because really it just went to the top and then it came back down. And this is supposed to be straight arrows. And I could call this V1, V2, and so on. Right, so it's just traveling along. Okay, so the part that we're trying to think about the most really is about the acceleration. So as it goes up, it's slowing down, and we've talked a lot about straight line motion. If something's going in a straight line and slowing down, the acceleration couldn't be in the same direction. It's got to be against the way the object or the thing is moving. If something's going in a straight line and going faster and faster, then the acceleration's got to be in that same direction. If we forgot about that, we could still use our old technique, and let's just say, let's compare V2 and V3. V2 is long and upwards. V3 is short and upwards. And so the change in acceleration is, what do I have to do to the earlier one to make it look like the later one? I've got to squeeze down on V2, make it shorter, and it's what I would have expected, that the acceleration is against the way that it's moving. In a straight line motion, if something slows down, the acceleration is always against the motion. If I look at the other side, I can do the same thing. I could take V6 and V7, let's say. So V6, short and downwards. V7, longer and downwards. I'm putting their tails together. I'm pretending I'm pinning them right there. And how do I make V6 look like V7? The earlier one look like the later one. Well, I've got to stretch V6. So the change in velocity that had to happen to make V6 look like V7 is this downward pointing change. Well, that's great. That's exactly what I would have hoped, is the acceleration points down when the ball is coming down. Okay? So far, so good. All right, so what about at the top? So what do you know about the ball when it reaches the top? All right, so I have this. At the highest point, we know there's got to be a moment in time at which it's not moving, because it's no longer going upwards. It's also not going down. It's changing its direction right there. So there is an instant in time, one instant at which the ball is not moving. So it has zero velocity right at the top. And you can see that, slowing down, slowing down, slowing down. In order to start coming back down, it has to stop and then come back down. The question is, though, does velocity equal to 0 mean that the ball also has 0 acceleration at that time? And a lot of people think that it does. A lot of people think that if there's no velocity, there has to be no acceleration. That's certainly true for this ball right now as it stays here. It's got 0 velocity. It's not changing its velocity. And if it's not changing, that means that it's not accelerating. Right? Because acceleration needs a change in velocity. Well, now here's where we can just kind of prove to ourselves that if you think about how we've done any of these problems before, as we've said, we need a velocity just before the point we care about and a velocity just after. And if we care about the top, that's this point, we can draw the velocity just before, take the velocity just after, and compare those two velocity vectors to see what the acceleration is. Well, what a lot of people do by mistake is they say, well, v4 points up. Well, that's not a mistake, that's true. v5 points down, and they put them like this, and they say, oh, look, they cancel out. Well, but that's not how we compare velocity vectors, is it? What do we have to do to the velocity vectors to be able to compare them? Well, we have to put them tail to tail. So v4 is short and up. v5 is short and down. So I put its tail at the tail of v4. And so to make v4 look like v5, I'm going to have to take the tip of v4 and pull it down so that it looks like v5. That means I still have my delta v pointing down just like I did in the other cases. So that means at the top, there is an acceleration that points down, and our technique that we've always used, right, the technique that we believe in, or we've seen that it works every time anyway, that's what it tells us over here, is that as it comes to the top, the v4 is up, v5 just after the top points down, put them tail to tail, the change in velocity is downwards. Now, that can still feel uncomfortable, but just think about this. When you ask yourself, what is the thing physically that's making the ball slow down? As I throw it upwards, physically what's slowing it down? Right? It's gravity. Gravity is what's trying to pull it back down. And here, if I started with the ball at rest, and I let it go and I drop it, it goes faster and faster because of gravity. Right? So the force of gravity between the ball and the earth is what's pulling the ball downwards. Does gravity stop at the top? Of course it doesn't, right? Gravity is always pulling it downwards. So what we're about to see, we're really close to the point where we can make that connection between understanding the acceleration directions tells us actually a lot about the forces that act on something. So in this case, even though it may not be what your gut instinct is, if we compare the velocity vectors, we do find that there is an acceleration downwards at the very top. And this is a tricky question that a lot of people struggle to understand until they go back to the fundamentals and think about what it is that's actually happening in this particular problem.